Thank you very much. Thank you, Luya, for the invitation and the introduction. It's very nice to be here. So I'm going to discuss compactness problems in counting special Lagrangians, and for their sections, most of the things I'm talking about are joined with Yang Li. Okay, let's start with the setup. And so the main problem I want to mention is the problem of counting some submanifolds called special Lagrangians inside some ambient spaces called Calabi-Yau threefolds. So let me start with the definitions. So by a Calabi-Yau threefold, I mean a manifold, a smooth manifold Z, where Z has complex dimension 3 or real dimension 6. So the complex structure defines an integrable almost complex structure J here. We have a symplectic form omega on Z. So omega is a symplectic structure on Z, and then these are compatible with a Riemannian metric G. So G is a metric so that these three are compatible. We also have an extra structure. It's usually called the holomorphic volume form. I denote it with omega. So omega is called the holomorphic volume form. So it's a non-vanishing top form, a complex holomorphic top form. So locally, maybe the best way to say it is that in complex coordinates, it locally can be written as dz1, wedge dz2, wedge dz3, where z1, z2, and z3 are complex local coordinates. And all of these data should be compatible. So the compatibility assumption is that if I look at my symplectic form and wedge it by itself 3 times, I would get a top form. And if I look at my holomorphic volume form and look at the same form, but just replace I with minus I get another 3 form there, which also would be a real 6 form. So the compatibility assumption is that they should agree. Up to a constant, they should agree. And this is just a problem of convention. You can rescale things for this constant to be whatever you like. So these for me are called Calabi-Yau threefolds. So this is the ambient space we like to study. And there are some submanifolds which are of particular interest in this talk. So definition, a half-dimensional submanifold inside Z. So for us, Z has real dimension 6, so L is 3 manifold inside Z. Is called a special Lagrangian if it's Lagrangian, so the symplectic form would vanish on L, and special means if we look at omega, it's a complex form. You can always write it as its real part, a real 3 form, plus I, imaginary part of the 3 form. So we would say it's special if this 3 form also would vanish on L. So it's being Lagrangian with an extra assumption. So this is defined originally, this definition comes from Harvey and Blaine-Lawson. So these submanifolds are kind of interesting. They're Lagrangian, but they're also compatible kind of more with the Calabi-Yau structure. In particular, these are minimal submanifolds. So if they're compact, they are absolute volume minimizer in their homology class. So that's our ambient space, and these are the objects inside the ambient space that we like to study. And there are many kind of proposals in the field to define kind of counting problems for Calabi-Yau threefolds by studying these objects. So there are many different proposals that the kind of idea is the following, that somewhat people like to start with a Calabi-Yau threefold Z and look at special Lagrangians inside Z. So this is special Lagrangian. And very, very loosely speaking, they like to count this set, right? It's kind of like trying to define a Gromov-Witten type theory, but looking at special Lagrangians rather than holomorphic curves. So this is a hope that this would make sense. The hope is that try to define potentially some Calabi-Yau invariant by doing this. So let me say a few words why there is a hope in doing so, why this should be interesting, and why this wouldn't really work as well as one would like, and what are the difficulties in addressing this. So the first thing is that being special Lagrangian, so special Lagrangian condition is a Fredholm, and it can be defined using a Fredholm operator, and because it's a 3D thing, it's a Fredholm condition with index 0. So that kind of motivates a counting problem. So that's the index 0 part, kind of means there is hope for defining a count of special Lagrangians. Although it's true that the index 0, but there is a theorem with kind of in the opposite direction. So it's due to Robert MacLean. So if you have a compact special Lagrangian inside a Calabi-Yau threefold, if you look at the nearby special Lagrangians, so if I define curly M sub L to be kind of nearby special Lagrangians. So this is, let's say, my 6-dimensional manifold Z, and this is the submanifold L, which is a special Lagrangian. If I look at small deformations of L, which are still their special Lagrangian, I get like moduli space of nearby special Lagrangians. This has dimension, the dimension of this space is B1 of L. So although it's an index 0 problem, it does not imply that this space is necessarily 0-dimensional. You might have a higher dimensional moduli of special Lagrangians. So this kind of might not look very good for a counting problem. So there are two ways to deal with such problems. So, so how to count? So the first one is due to Joyce. So Joyce's proposal is that, well, let's fix a homology class in the third homology of Z. And in that homology class, let's only look at special Lagrangians, which they have B1 equal to 0. So these are essentially rational homology 3-sphere special Lagrangians inside Z. And because B1 is 0, it kind of means they're isolated. They don't have any deformation. And since they're isolated, it kind of makes sense to hope that we can count them. So that's one proposal. The other proposal is that, well, if it's an index 0 problem with suitable perturbation, one can hope to get to some sort of transversality. So that theorem says no matter how much you perturb the Calabi-Yau structure, like all of these J, omega, G, and the other omega, the space of nearby special Lagrangians always have dimension B1. So in some sense, it says you can never get to transversality as long as you keep the Calabi-Yau structure a Calabi-Yau. The reason is that the space of Calabi-Yau structures, unlike the space of, say, almost complex structures, is a finite dimensional space. So if you really want to get transversality, you kind of should perturb your structure outside of realm of Calabi-Yau stuff. So, but still there are some kind of subtle difficulties here. So there is one proposal how to get this transversality due to Donaldson and Segal. And this kind of has been carried over by Emily Hutton wins. So one can get either transversality and count all special Lagrangians. Hopefully one can count all special Lagrangians, or one can just look at the things which are rationally homology 3-sphere and count those which are isolated. Anyways, I'm sure there are other ways to get transversality, or even if it's not a zero moduli space, there are other ways to extract invariants. So these are just two examples of how one might do that. So there is a kind of a more serious difficulty in counting special Lagrangians, and that's related to kind of compactness, wall crossing, formation of singularities, and things like that. So suppose we have Z, a Calabi-Yau threefold, but suppose now we start to deform our Calabi-Yau structure. Suppose we have a one-parameter family of Calabi-Yau. I just mentioned omega and J. Suppose we have a one-parameter family of Calabi-Yau structures. And this is like the time direction. And at each time, suppose I'm counting my isolated special Lagrangians, okay? So this is a possibility that you have one special Lagrangian for some time t, and then as you perturb your Calabi-Yau structure, you can perturb your special Lagrangian so it stays special Lagrangian with respect to deformed Calabi-Yau structure. However, this is possible that at some unhappy time, t equals 0, your special Lagrangian becomes singular. So it forms a singularity. And a possibility is that as you kind of continue to deform your Calabi-Yau structure, your special Lagrangian would kind of resolve its singularity, but it would resolve the singularity in two different ways. So in some sense, after this t equal to 0, you get two special Lagrangians coming out of that. So you had one special Lagrangian, say L1, and at some time becomes singular, and it's like you have a wall crossing phenomenon. After you pass some special time, you get two special Lagrangians. The converse is also possible. You might have two special Lagrangians in your Calabi-Yau threefold, and as you're perturbing the Calabi-Yau structure, they might closer and closer to each other, and at some time, they might hit each other, and after that, they might give you one special Lagrangian. So this kind of suggests a naive count would not stay invariant. So this can happen. This can happen. I think there are many people who worked on this, but maybe mentioning one person would be Dominic Joyce. The point is that this can happen, and the implication is that it's hard to expect a naive count. Naive count would not give an invariant. Okay. Any question up to this point? Are we happy with the setup? Okay. Okay, so there are two essential questions here. One is that, so question number one is that what types of singularities can arise, or how does this happen? So I said at this point, you get singularity and the number would change. What is this exact change in number, and what types of singularities would arise? So what special Lagrangian singularities we would get when we are perturbing our Calabi-Yau structure in a generic one-parameter family of Calabi-Yau structures. And then the second thing is that after understanding this, the second thing is that, is it possible to define some weight or some multiplicity that if we count special Lagrangians with that multiplicity, then we would get an invariant. For instance, is it possible when we have our Calabi-Yau threefolds and L, rather than counting L as, say, plus or minus 1, we would count it with we would assign some, say, integer maybe to that. So in that setup, the integer associated to the weight associated to L1 would be equal to the weight of L2 and L3. And maybe that would kind of help us to get an invariant. So looking for a weight which either gives us an invariant or kind of it would change in a very tame, understandable way is something people are looking for. So in the most naive sense, one hopes to find an invariant in Z. If we have time, I would mention it seems unlikely at the end to expect a Z invariant thing, but it's expected that maybe a kind of a homological invariant can be assigned by considering all special Lagrangians that it's expected that would work. Okay, so let's leave this here. So the first question is a hard question, and there are conjectures what types of singularities can arise. One of the most promising approaches is due to A, B, C, D, is due to Donaldson and Scaduto. You can consider, rather than thinking about any Calabi-Yau threefold, we can consider simpler Calabi-Yau threefolds. So suppose we have a Calabi-Yau threefold Z, but suppose it has an extra structure. So suppose it has a kind of fibration over a two-sphere, where the fibers are K3 surfaces. And some fibers might be singular, right? And the fibration is Lefschetz fibration. So you might be familiar with Lefschetz fibration of symplectic four manifolds with a complex or almost complex structure. This is kind of a similar thing, right? The dimension also makes sense. We're writing our six-dimensional object as 4 plus 2. This is not the case that it's not true. There are Calabi-Yau threefolds that do not admit such Lefschetz fibration, but there is a very interesting family of Calabi-Yau threefolds that they admit such Lefschetz fibration. So let's consider these and as a kind of model or example, look at special Lagrangians in K3 fibered special Lagrangians. Okay, and we know what is K3, right? With that, okay. So let's say as an example, we are hoping to kind of study the space of special Lagrangians here. And kind of examine those two questions in this setup. So when something is fibered, one thing one can do is to start to, so this is fibered over CP1. One thing one can do is to start to collapse the fibers. So suppose I'm deforming the Calabi-Yau structure and the corresponding metric in a way that the base direction would not change, but the diameter of the fibers start to shrink. So suppose I am doing a deformation where my Calabi-Yau is like this first, and then I would shrink it a bit more. It becomes like this. And then in the limit, I completely shrink the fibers, and the diameter of the fibers would go to 0. And when I do that, I collapse to the base. When I completely collapse the fibers, the only thing which would survive would be whatever base was. This kind of shrinking is called adiabatic limit. So something Donaldson and Scaduto started to analyze was that to look at special Lagrangians here, which are complicated and we don't know what special Lagrangians here look like, but kind of suppose we know something about them, and suppose we are kind of tracing what happens after shrinking. So what would special Lagrangians project to after we completely shrink the fibers? This should be something on CP1. So this was my Calabi-Yau threefold fibered over CP1. The local model is, well, S2 locally looks like R2, right? So let's say locally, if I just look at the chunk of the base, not the whole thing, let's look at some subset of S2, which kind of looks like R2. I'm just looking at the chunk of, say, my Calabi-Yau threefold. And I don't know what special Lagrangians here are. I have my K3 fibers, and after collapsing the fibers, I would collapse to the base. If it's compact, it would be S2. If it's non-compact, it can be something like R2. So the observation Donaldson and Scaduto had was that when you collapse, the special Lagrangians will project to trivalent graphs here, like some edges and some vertices, but the degree of vertices is 3. That's the observation. And then using this, they try to conjecture what were the special Lagrangians in the Calabi-Yau threefold that after collapsing, they would project to these trivalent graphs. So let's look at this and try to guess what the special Lagrangians were in the original Calabi-Yau threefold. Okay, so well, I can think about that base as the same as this one. After collapsing the fibers, my manifold would become this base. And let's say my special Lagrangian would project to some trivalent graph. So they formed a conjecture by looking at this picture. So it's not very hard to see what happens above each edge. So K3 surfaces are holomorphic objects, and they have holomorphic curves inside them. So the expectation is that above each edge, you have like almost a cylindrical object, which is kind of result of following holomorphic curves inside K3 fibers. So it's like a cylindrical object where on each fiber, well, loosely speaking, above each point, you have a K3 surface, and the part of special Lagrangian which would collapse to this specific point would be a 2-sphere. So maybe I can write the expression here. So we have the model cylindrical special Lagrangians. So let's say for simplicity, although Z is a kind of K3 fiber, let's say for a second for simplicity, it's K3 times, say, S2 or maybe even R2 or C, just as the model. So if you pick a holomorphic curve, this sigma is kind of a holomorphic curve inside K3, one can pick a good ray inside C. So thinking about C as R2, one can pick a good vector V in R2 so that R times V, this ray, would be essentially a line inside C. And this product is like a cylinder, right? It's a holomorphic curve. If we multiply that by a ray, it would be like a cylinder inside K3 times C. So this is a model special Lagrangian. This is a cylindrical special Lagrangian. And where does this direction come from? So K3 has hyperkähler structure. So it has many different holomorphic structures. It's not fixed. And that direction is actually kind of related to that. That holomorphic structure tells you what direction you should pick. But anyways, the bottom line is that above each of these kind of edges, the expectation is that the special Lagrangian you have that would project to that edge is of this form. So you would expect to have inside your Calabi-Yau threefold, you expect to have 3 cylindrical special Lagrangians coming together. And what would happen above the vertex? The natural guess, if you look at this picture, is that there should be some probably special Lagrangian like this projecting to that, right? This is called a pair of pan special Lagrangian. If these are, say, 2-sphere, This is called a pair of pants. So special Lagrangian pair of pants. So this motivated Donaldson and Scaduto to conjecture existence of pair of pants special Lagrangian. So let me write the conjecture here. So Donaldson-Scaduto conjecture. So let Li to be sigma I times RVI inside K3 times C, where I is 1, 2, and 3. We have 3 cylinders, and each sigma I are holomorphic in K3, in hyperkähler K3. So that there is a topological assumption, the sum of the homology classes would vanish. Then there is a pair of pants special Lagrangian L inside K3 times C with 3 ends asymptotic to each L1, to these 3 L1, L1, L2. So loosely speaking, it just says you can glue these 3 special Lagrangians to get this pair of pants. This is an interesting conjecture, because once you construct these pair of pants special Lagrangians, you can start to glue them to make more and more complicated special Lagrangians. That's one reason why it's interesting. It gives a very good description of the moduli space of special Lagrangians in K3-fibered. So K3 times this kind of local model of K3-fibered Calabi-Yau threefolds. It's not, you hope by a perturbation and deformation from the product to go to more generic setup. The other reason is that I mentioned expect wall crossing related stuff, how the number of special Lagrangians would change. So it's much more promising to, rather than looking at special Lagrangians and see how they would change when we are perturbing the Calabi-Yau structure, it's much more promising to look at their limit as graphs and see when we are changing the Calabi-Yau structure, how these trivalent graphs would change. So if we construct these, we are kind of getting one-to-one correspondence between these trivalent graphs and special Lagrangians. And you hope to kind of turn a lot of more topological, geometric stuff into more combinatorial descriptions. So by looking at the graphs and their change, prove theorems about special Lagrangians. So that was, I think, the Donaldson-Scaduto part of their motivation. Also, I think a variation of this conjecture with slightly different, was conjectured by Andy Knightsky, maybe in 2013. This is more recent, but more closer to the what I want to talk about. So this conjecture in this generality is still open. This is conjecture for any hyperkähler K3. This is any hyperkähler or any generic hyperkähler K3 surface. There's a local version of this conjecture, which is now proven. So I don't want to go into much analysis details about this. So let me state it in a kind of rough sense. But the point is that there is a moduli space of hyperkähler K3 surfaces. And it says no matter which K3 you pick, the conjecture should be correct. But if you look at the space of hyperkähler K3s, so each point here is a different K3, different hyperkähler structure on the K3, there is a boundary of this space, which let's denote an element on the boundary X, which has a very special description. So I just write it because it's a bit, maybe not exactly in the direction of my talk, but let me just say what it is. So what you can define X to be A2 type resolution of singularity of a singular K3. That's one description. Another way of saying it is that ALE3 gravitational instanton. Another way of saying it is given by Gibbons Hawking answers. But these are not very important. Loosely speaking, you can think about it as some special kind of degenerate K3. So there is a conjecture which is exactly the same thing, but rather than saying for every K3, you replace K3 with a kind of more special hyperkähler manifold X, which X is this. This is called local Donaldson-Scaduto conjecture, and it's correct. So theorem, which is expected to prove the conjecture at least for an open subset of K3 surfaces. That's been the motivation of this conjecture. So theorem with Yang Li is that the local Donaldson-Scaduto conjecture holds. Maybe I just say something about proof in one line. Maybe I write it there. So we have our Calabi-Yau threefold, which is K3, let's say times C, and is projecting to C. And we have three cylinders. These are given L1, L2, L3, and we want to say there should be some special Lagrangian kind of asymptotic to these. A three manifold which kind of looks like this. And each of kind of this would project to this trivalent graph after completely collapsing. One observation is that if we collapse, you would get the trivalent graph. But if we don't collapse and project, this would project to a neighborhood of this graph. So the projection of this conjectured special Lagrangian would be expected to be something, I hope I can draw it well. This is supposed to look like an amoeba. Maybe I do it here. This is, I think, usually called amoeba-like thing. So this would project to a neighborhood of the graph. This is the expected thing. Okay, so if you project, but not completely collapse the fibers. So one like to say there is such special Lagrangian, so we are looking for this. The kind of strategy of the proof, I'm very, very vague, but is to write down the equation that would describe this Lagrangian, this special Lagrangian. So what PDE described that? It turns out it would be a real singular Monge-Ampere equation. And these asymptotics would define the boundary value of the PDE, which would be a Dirichlet type PDE. Then one, in order to show this submanifold exists, one should solve this equation. And solving it would follow from the works of techniques of Taffarelli and maybe Mooney and others. And then when you do that, you get a special Lagrangian, but from analysis, you wouldn't be able to get the special Lagrangian is smooth. If you want to say it's an embedded smooth submanifold, you have to do really geometry. The ingredients here come from geometric measure theory, in particular from the works of Allard. And then some analysis of special Lagrangian, which is essentially based on the works of Joyce and works of Mark Haskins. Anyway, one can do this, solve the equation, and show there is a special smooth special Lagrangian here with a pair of pantopology kind of asymptotic to this, which kind of essentially means you can glue these edges together and construct a lot of special Lagrangians projecting to these. So it kind of verify conjecture of Donaldson and Scaduto that before collapsing, there were really such special Lagrangians projecting to those. Maybe just one. Is there any question? Yeah.
So this A2 thing, this is like, it's got only two holomorphic spheres in it, right?
It has three.
What's the third?
You can, it depends on, in Gibbons-Hawking construction, it depends on how many points you pick to define your harmonic function to be constant plus sigma 1 over distance from those points. Here I picked 3 because that's the generic case. For 3, you have 3 holomorphic curves and 3, you should pick 3 rays in R2, and that's the product of 3 cylinders. It comes with any n. Maybe that's a good thing for me to mention. Thank you. You could have more than 2 cylinders coming, more than 3 cylinders even coming together. You could pick AN type ALE space, and you would have, or ALF even. You can have n cylinders coming together. It's usually called the generalized Donaldson-Scaduto conjecture. Our proof actually extends to this. So we actually prove even if you have n things coming together, you can form this. However, this is not very important because it's not generics. Because if you get that, it means you had more than 3 edges coming together. And you expect if you perturb a bit, one of them would move somewhere else, which is essentially the result of gluing again 3 cylinders. Does that answer the question?
Sure.
Okay, great.
I wanted to ask about so that you mentioned there was some moduli given by B1 of L. So if you prove this, then
that was compact. That was for compactness. My next statement is about that. So the point is that I said we are interested in counting special Lagrangians. So related to what Luya mentioned, and the problem she's thinking about, you might hope to be able to count suitable graphs here if you have a good one-to-one correspondence. So you turn your counting problem into a more combinatorial one. Something in that direction you like to prove is that if there is such graph here, there is exactly one special Lagrangian projecting to that. So we proved there is one, but maybe there is more. If there are more, you don't get one-to-one correspondence. So this is also conjectured by Donaldson and Scaduto. So there is uniqueness in the local Donaldson-Scaduto conjecture, and this is correct, and it's a theorem and a paper with Bora and Yangley. So the point is that the deformation, so it wouldn't be exactly B1 for a non-compact one, but the point is that you can see it doesn't admit any deformation, but uniqueness is more than that, because there is a chance that there is no deformation, but there is a chance that far away there is another special Lagrangian with suitable asymptotic ends projecting to the same thing. So you want to say there's just one special Lagrangian projecting to this. It might be far away from this one, so it wouldn't follow just from deformation here. Yeah, okay. Actually, this is also
uniqueness is conjectured in the non-local problem.
It is conjectured in the non-local. You see, we did analysis here and proved this using PD method. I don't think PD method would be enough to prove it in the general case. It's expected you would need some more Floer-theoretic way, similar to the work of Imagi and Abu Zaid. Yeah, but it's conjectured in general, but probably more topological ingredients are necessary. Here we really did maximum principle and analysis, things like that.
Then in your bifurcation picture at the very beginning, is that you have these graphs and the graphs will just separate out.
You mean the graphs on the base?
So you have this, or there's an underlying graph picture.
Yeah.
And then if you come and you change all the data, then the graph splits.
That is the motivation. So exactly. So there is so for graphs, you see, when you collapse the manifold, you get some structure and some graphs on the base. And these conjectures about what type of singularities appear on special Lagrangians there's a dictionary to say what happens in the graph picture. And Donaldson and Scaduto verify those for graphs. So if you can make a complete dictionary, you expect to, by that dictionary, get proof for special Lagrangians. Yeah, these are much more like straightforward for graphs. That's the hope, to get all those theorems for special Lagrangians. Also, I should say this is a kind of also like a compactness theorem by itself, or a compactness conjecture / theorem. Because in the conjecture, they say any hyperkähler K3 you pick, or we say these spaces have a lot of deformation. They have a higher dimensional moduli space. So it says no matter how you perturb these, you have this, as long as it's generic, you have this fixed special Lagrangian. In this setup, you would not form any extra singularity. So it's kind of like a compactness theorem by itself. Yeah, so this is kind of a promising approach to answer the first question and reduce the singularity formation to combinatorial setup. Let me say a few words about the second problem. Could we define some weights on special Lagrangians that counting special Lagrangians with those weights would make sense or not? So I mentioned the integer valued one. If we have extra time, I would mention why probably the integer valued approach would fail and why one might expect a Floer-theoretic thing. But let me very schematically say what is the expectation. So the expectation is that when you have your special Lagrangian, which is let's go back into the global setup. So again, we have a compact Calabi-Yau threefold and a compact special Lagrangians inside it. We are not in local model anymore. And I want to see what the weight should be. So it's kind of conjectured in some sense. One like to count the number of equations to some the number of solutions to some equation on L. So there is, so schematically, you're looking at some PDE type on L. So schematically, it's like looking at maps from L to some other manifold. Let me say what this other manifold is. Let me denote it by XAH. That F satisfies some equation. It's called Floer equation. So let me say this very, very vaguely. So X here, suppose you have a manifold X, which the dimension is multiple of 4. So in the simplest case, let's say it's a 4-dimensional manifold. And suppose it has hyperkähler structure, which means it has 3 different almost complex structure, IJK. You can assume they're integrable. So they're almost complex. Also, they have this property that they satisfy quaternionic relation. So if you first apply J and then I, it's like applying K. Okay. And suppose we have a domain 3-dimensional manifold. And I would say F is a Floer map, or sometimes called Dirac, solution to a Dirac equation. If at any point I pick on my base 3 manifold, let's say this is L, at any point X, if I pick an orthonormal basis, E1, E2, E3, if I look at derivative of F acting on E1 and then multiply that by I, plus the F acting on E2 multiplied by J, plus the F acting on E3, with K, it would be 0. So df of EI would be a vector here. You can act by IJK. This makes sense. So this kind of should be understood. I guess Simon knows better, but I think it should be understood as a higher dimensional version of holomorphic curve equation, right? It's kind of like the holomorphic curve equation, but your base is 3-dimensional. One should be a bit more careful. This is a bit schematic. The point is that rather than thinking about maps, one should look at sections of some bundle, but this is kind of the local description. So rather than, it's kind of like sometimes rather than looking at holomorphic maps, you look at holomorphic sections. So there's something like that going on here, but let me not mention that. So loosely speaking, we want to count these. What is X? So there is a very, very specific X which they propose here. So X is something called Atiyah-Hitchin 4 manifold. It's a hyperkähler four manifold, so it has ijk. It has some non-trivial topology, this four manifold. And the essential thing is that it's asymptotic. So if you cut a compact part of it, asymptotically, it's very, very close to S1 times R3 mod Z2. So there are different ways to define this. This is not very important for our setup, but one can define this as a space of rational maps on CP1. There is a way to define this as the space of moduli space of monopoles on R3, or moduli space of translation invariant instantons on R4. But anyways, the thing I want from this, that it's a non-compact four manifold. It has three complex structure I, J, K, and it's kind of asymptotic to S1 times R3 mod Z2. So they propose a very, very specific four manifold. And they say, when you have a Calabi-Yau threefold, let's say you have some special Lagrangians L1, L2, L3, etc., and you want to count them, don't count them as plus minus one. Count them, assign an integer to them. What is the integer? It's the number of maps from that three manifold to this four manifold that satisfies this equation. So this might sound a bit weird. Let me spend maybe a minute to say why they proposed this. Why do they expect this to give you something interesting? And then mention the main difficulty in following their proposal. So why do we propose these weights? So if you're familiar with Taubes, Seibert-Witten equal Gromov on symplectic four manifold, you kind of have seen something in this direction. If you have a symplectic four manifold, we can define an invariant by looking at solutions to Seibert-Witten equation, or we can do a variation of holomorphic map, curve, current counting, and Taubes theorem says they would agree. Something like this is expected to, this is like a duality, where on one side you have gauge theory, and on one side you have submanifold theory, which in this case you have holomorphic curves. These dualities are expected to happen in higher dimensions and on different manifolds. The most general version, to my knowledge, is proposed by Tian. And there is a very special example of this duality, which is expected to hold here, which is a version of this Tian duality between gauge theory and submanifold geometry. This is called Donaldson-Segal conjecture. So Donaldson and Segal define, so let's say you have a Calabi-Yau threefold, they propose a gauge theoretic invariant. So I will just write the name, so it's just a name for us, I did not define this. They're called Calabi-Yau monopoles. And they propose counting solution to this gauge theoretic equation might give you an invariant on Calabi-Yau manifolds, similar to Seibert-Witten invariant of four manifolds, let's say. And on the other side, we have this count of special Lagrangians, a weighted count, not with weight one, but a weighted count of special Lagrangians. And they conjecture similar to Seibert-Witten equal to Gromov, they want this equality to hold. But if you try to make this work, the weight would actually be forced to you. And that weight is exactly this. So if you want to have kind of top Seibert-Witten equal to Gromov on Calabi-Yau manifolds, this is kind of forced to you that you should count your special Lagrangians with these. One more remark, and then I say the main theorem. The next remark is that independent of this Donaldson-Segal conjecture, in I think around 1999, Taubes had a paper called, I think, nonlinear Dirac operators over three manifolds, where he tries to introduce new three manifold invariants. One of the invariants he defines is exactly like this. So completely independent of this Calabi-Yau and special Lagrangians, we have a closed oriented three manifold, and he wants to propose an invariant. He exactly suggests, look at, again, not maps, but sections, but for simplicity, let's say this, maps from L to a hyperkähler manifold, which they satisfy this equation, and count the solutions. this equation would make sense for any hyperkähler manifold, but again, for reasons motivated by Rosansky-Witten theory, he suggests to take X exactly what appears in the Donaldson-Segal set. He suggests this should be Atiyah-Hitchin. And some physicists told me this count should agree with another well-known invariant of three manifold related to Rosansky-Witten invariant. But I mean, physicist. I'm not sure how accurate that is.
How important that this manifold is hyperkähler and not just like hypercomplex? Almost.
For the next theorem I'm going to mention, which is compactness problems, it's quite important. For defining the equation, is just like you define holomorphic curves in any, but let's say you wanted to define Gromov-Witten theory for almost complex manifolds, rather than almost complex structure compatible with some omega. So here, at least you want your ijk to be compatible with some omega 1, omega 2, omega 3. That's the least you want. There is another difficulty which I would mention, right? Yeah.
There's a notion of a triple of symplectic forms taming a triple complex structure.
That is correct. Yeah, but yeah.
And whether you can prove compactness is up to, I mean, so far it's proven in so few cases that people use like very specialty.
That is correct, yeah. I'm going to mention exactly those few cases, but yeah, it's more towards the analysis rather than just the notion. I mean, there are conjectures in the field. I guess you know more about those, but yeah, that you can extend it to much more general setup.
So this counting is only dependent on the quality of it, or what?
So, you know, you are saying E1, E2, E3 are orthonormal. So you're potentially dependent on the metric. There are two things. For Taubes proposal, you expect this at the end to be invariant of the metric. To get topological three-man. In Donaldson-Segal, that doesn't matter much because Calabi-Yau manifold comes with a metric, and just restricting that to submanifold defines a metric on the submanifold which can be used here. But it's related to a compactness theorem. I'm going to say a few words about compactness, right? Any other question? Very good questions. Okay. Yeah, so both for Donaldson-Segal conjecture and for Taubes proposal, the essential question is this count finite or not? So, I mean, is it finite? So if this set is a finite set, then counting it would make sense. Also, there are Floer-theoretic version of these. For instance, I have a paper on, I call this monopole Fueter Floer homology. You can think about the Floer homology essentially generated by these, and that seems to be more promising for defining Calabi-Yau invariants. But anyways, so let's answer this question. So suppose you have a sequence Fi of these maps. And you hoped to say there is a subsequence kind of converging to another one of these to get compactness. So if you assume a bit more, if you assume there is a Dirichlet energy bound, and then there is also L infinity bound, you get a kind of a compactness theorem. I should say some difficulty here is that your target is not compact. So possibility is that you have maps from your three manifold to this, a sequence where their image just goes to infinity. So that's a possibility. The target not being compact is the main difficulty. So is this correct or not? There is a theorem of Walpusky that says this is almost correct. You get convergence, C infinity log convergence, but not everywhere on L, on complement of a closed subset. So let's say this is our three manifold L, and we have a sequence of these maps, Fueter maps. We would, just like holomorphic curves, we expect maybe some bubbling and things like that, and that's true. So the kind of formation, we get formation of singularity along two sets. One is Z naught, which is essentially is expected to be a collection of singular points. These are called non-removable singularity. And then one is C1, which is bubbling, but bubbling is always co-dimension two things. So if above on holomorphic curves, you get bubbling at points, on three manifolds, you expect to get bubbling along one-dimensional things. So bubbling. And Walkuski's theorem is not for this, is for any hyperkähler for manifold, or for K manifolds for any hyperkähler. And on the complement of these, you get compactness. So these are the only things which can kind of go wrong. So, theorem, if we have these two assumptions, if star holds, and if we restrict the hyperkähler manifold to be the one which appears in Taubes and Donaldson-Segal conjecture, we get an honest compactness theorem. There would be no bubbling and no formation of singularity. So that's a good thing. And then the remaining challenging case is when you don't have these assumptions are not natural. When you want to count, you can't say, let's assume the energy is uniformly bounded. Why is that? So unlike the theory of holomorphic curves or instantons where the energy is a topological invariant, for Fueter sections, that's not the case. You can have a Fueter section with image in a certain homology class. And if you are actually section, this is kind of important, but the thing which appears here is section rather than map. So it happens, in fact, we construct examples where you deform the Fueter section just a bit and the energy blows up. This is in contrast of the case of really maps, which there are energy identities. So there is no topological energy bound in these two conjectures. So if you assume these, you get compactness, but in general, you are not allowed to assume these. And if you don't assume that, it can happen that both L infinity and L2 energy of derivative blow up. If that happens, you can always in geometric analysis, if something blows up, you would rescale it with the thing which is blowing up. And if you do so, these Fueter sections with blowing up thing, in some suitable sense, would converge to something called a Z2 harmonic one form on the three manifold. So the compactness doesn't hold, but if you have a sequence which goes to infinity, after rescaling, it converges to a model. This is expected to help us to kind of compactify the space. And this can really happen. So in the simplest case where the three manifold is a Riemann surface times S1, if we add the extra assumption that the Fueter map is S1 invariant, the equation would reduce to a holomorphic section equation. Because you have a map on the three manifold, you assume it's invariant under the S1 rotation, it reduces to an equation on the fiber and turns out to be a holomorphic one. And we can explicitly solve that. And just by looking at those, we can see you get a non-compact space of things that the L infinity energy really blows up. And so I don't want to go into the proof. The proof is essentially based on something called Lefschetz approximation method, which is due to Almgren, or more recently, the Spadaro and Delelis. And it's a bit similar to, it's a non-linear version of Taubes' work on studying solutions to Kapustin-Witten equations and relations to Kovanov homology or Jones polynomial. Anyways, so we still don't have an honest compactness. We have a compactification way. And actually, people tell me it might be enough for defining a Floer theory one, although we lack the compactness theory. Okay, I guess it's a good time to start.
Can you explain in like a picture why Z2 harmonic one form?
Yeah, so
you're going off to this piece.
It's exactly this, yeah. So
there's an S1 factor.
Which
it's not like a Z2
would that be
mod
important?
Z2. What's the difference? Yeah.
Yeah. So the S1 factor turns out wouldn't be important, so ignore that part. If you have a map to this, it has the S1 part and R3 mod Z2 part.
Yeah.
The S1 part turns out to be almost constant.
Oh,
So this only matters. But I mentioned this is not a map section, and the section you should pick, the honest thing which I never defined is that when you have a 3 manifold, you have the frame bundle over that, which is an SO3 bundle. And then SO3 act on this space X. So rather than maps, you should look at the associated bundle to the action of SO3 on this thing. And the Floer equation for the sections of this bundle, literally in the limit, implies you get a further section of associated cotangent bundle mod Z2, loosely speaking. The difficulty is really on the details analysis. So when this is very large, the error becomes kind of large and your further sections would start to lose being Lefschetz and you can't get limit as kind of geometric analysis difficult. But intuitive reasoning is really just comes from this.
And you said integer may not.
Yeah.
In this case.
So if you were to look at literally all special Lagrangians, suppose any oriented 3 manifold could appear, similar to the problem that you're familiar with in the G2 setup, that things can come together and form connected sum, things like that. Essentially no integer valued thing would satisfy those equations. This is something similar, but the Floer-theoretic version is expected to handle this in the special Lagrangian case, though, not in the G2 associated.
And we have announcements. Oh, actually, wait. So maybe let's thank the speaker first.